In this section, we're going to look at problems with constant acceleration, and very specifically, we can think of these as constant gravity problems. It turns out that gravity is constant on Earth or in any planet near the surface. That means within a pretty large range, we can assume that the acceleration is going to be the same. That's within, a large number of feet to tall buildings. You'll never see the gravity change. Now, if you go up really high, and obviously if you get to outer space, then you'll find that the acceleration due to gravity is zero. There's no acceleration because there's no gravity out there. But near the surface of the Earth, the acceleration due to gravity is 9.8 meters per second squared, or 32 feet per second squared. You must memorize both of these numbers. That's the acceleration due to gravity near the surface of the Earth. In many of the problems that I work, when I practice with you for problems, I'm just going to take G is equal to 10 meters per second. Or I'll take G is equal to 32 feet per second. I'm rounding this 9.8 off because actually 9.8 is not exactly right. But if we just want to get across the concept of how we work these problems, then of course this is very sufficient. And the 10 lets us work really, really fast because we don't have to worry about this 9.8. So now what is it I'm saying? If we take any object, and this was first determined by Galileo, no matter what the mass, this could be a cannonball, and this could be a much lighter object. This could be very, very solid. This could weigh 1,000 pounds, and this could weigh 1 pound. As we drop these, it turns out they fall exactly together. The acceleration is the same for every mass. And later we'll understand why that occurs. It's because gravity is proportional to the mass, and the acceleration is the force divided by the mass. So the mass cancels out. So the acceleration of both of these masses, of any two masses, is the same. Now let's assume that we're in a vacuum. Obviously, if you have a feather, the air resistance is going to put an upward force on it greater than a cannonball. But other than that, if we're in a vacuum, like if we're on the moon, a feather and a cannonball are going to drop at exactly the same rate. Now, one thing about motion is that we can always assume that at the top of our motion, like if we throw something up, right up here, what happens? Well, it starts out with a velocity, let's say v0, or equivalently v of 0, either way you want to write it. At our initial velocity, we're going to have an acceleration in a downward direction. That means we're going to be slowing down until finally, right up here at the top, what happens to the velocity? The top is specified by having a velocity equal to 0, right at the top. Then the object turns around, begins to come back down. When it gets down to this exact same place, the velocity is going in the opposite direction at exactly the same magnitude. So if I throw something upward at 8 feet per second, then it'll go up here, and when it gets to the top, it'll be moving at a velocity of 0. And then it'll fall back down, and when it gets to this position again, it'll again be moving 8 feet per second, but it'll be moving downward rather than upward. That's a very important point to remember, because often on tests you find that one will ask you, what's the velocity of the particle at the top? And the answer is 0. And they'll say, what is the acceleration at the top? The answer is, the acceleration is always the same. It's always 9.8, or let's say 10 meters per second, or it's 32 feet per second squared. So the acceleration doesn't stop at the top, and many students miss that. And it doesn't get faster down here. Acceleration is constant, all the way up and all the way down, and never changes. It's the velocity that's changing. 8 feet per second down here, goes up, finally it slows down to 0, and it goes back up to 8 feet per second as it falls. Now, one example I like to give is if you go to the moon where there's no air resistance, and you sit there on the moon, and you take a gun, you shoot it upward, the bullet leaves, of course, is the muzzle velocity of the gun. So it's very fast. It would kill you, of course. The bullet goes all the way up. It will then stop at some point and fall back. When the bullet falls back down for that same distance, it will fall at the same rate that it had when it left the gun. In other words, if that bullet falls on you, it'd be just like you pointed the gun at the top of your head and shot yourself. So that emphasizes the fact that the bullet goes up, slows down, stops, turns around, comes back down, and speeds up. It's a good way to remember it and think about how that works. Remember, acceleration A is equal to G all the time. The velocity when the object falls again to the same height is the same example. And I'd like to talk to you just for a moment about terminal velocity. If you jump out of a plane and you spread yourself out like this, there you are, old spread eagle, and as you fall, making yourself as exposed as possible to the maximum drag you could get, it turns out that you'll go at about 140 miles an hour. Something that would certainly kill you if you hit flat at that rate, which you don't want to do. But if you stood up and removed that air drag, you'll go at about 240 miles an hour. So if you're just going down like this, you're going to move at about 240 miles an hour, almost twice as fast, 100 miles an hour faster. So now what we need to do is we need to work some of these problems that concern gravitational speed, and we need to apply the questions that we had, the equations that we had earlier, and that's what I'm going to do at this point. Okay, so now what do we know on these constant gravity problems? We know our constant A is equal to either 10, we're going to round off that 9.8 meters per second, or it's equal to 32 feet per second. And that's squared. You notice that this equation looks like it's incorrect, but this is 10 in meters per second squared, this is 32 in feet per second squared. So this is a totally valid equation because the units make up for the difference between the two numerical values. Let's look at a problem where I just take a building, and the building might be some height. Let's say it's a height of 64 feet. And we're going to take an object and we're going to drop it off the top of the building and see how long does it take to get to the bottom. Well, we want to know the best way to work these problems is first of all list what do you know, and along with what do you want to know. So I'd say, what do we want to calculate when it comes down here? We want to know the time when it gets to the bottom. We want to know the velocity when it gets to the bottom. In other words, we want to know the velocity finally. I'll put a velocity with final. We know the distance is equal to this value here. We know that the acceleration is equal to, since I'm using feet here, I'll want to use 32 feet per second squared. And we know something else. If we just release this object right here, we know the velocity initially is equal to 0. Now you'll notice I've put down everything that I know. I know the height of the building. I know the acceleration due to gravity. I know we just released the object, so the initial velocity is 0. And I say, what do I want to determine? I want to determine the time when I get to the bottom, and I want to determine the velocity when I get to the bottom. There's nothing else to know. Well, how would I do this problem? Well, if I look at this last equation, it doesn't involve the time. And that last equation is very useful then because it would say the velocity at the new time, finally, squared, minus the velocity initially, which is 0 squared, is going to be twice the acceleration. The acceleration is going to be what? Acceleration is going to be 32 times the distance, which is 64. Now, if you look at that carefully, you can see I rigged the numbers so that this is going to be 64 times 64, or velocity final squared is equal to 64 squared. We can take the square root of both sides and see that the velocity final is equal to 64. And that 64 is, of course, going to be in feet per second. Now, how did I do that? Well, if I don't need the time in the equation, then in fact this last equation doesn't involve the time, and I can just use velocities, acceleration, and distances, which is what I did. But if I want the time, then I would have to work an equation like this. The reason I couldn't use this one is I don't know what the final velocity is, so I couldn't use this equation here. I would have to say, oh, I know the distance, so I could set this up as saying, to find the time that I get to the bottom, I would go a distance. Let me just write these values out. The distance would be 64. That would equal to the initial position, which is 0 at the top, 0, plus initial velocity of 0 times t, plus 1/2 a times t squared. Well, if I look at this, then that is something I can rather easily solve. My acceleration is 32, and half of that is 16. So I've got 16t squared. And if I take 16, and 16 is 32, 32 is 64, it goes into that 4 times. So t squared would be equal to 4, and t is therefore equal to the square root of 4, or 2. So this object is going to be in the air 2 seconds. And you might ask, well, isn't there another way I could work that? And the answer is yes, there is. I could have worked that problem the same way by using this equation if I use this one first. Determine the final velocity. I did that right here. And then plug the final velocity in here. So let's try that. Let's now say, well, I've already used this one to get the velocity, which is 64. And the velocity is going to equal to 0 plus acceleration 32 times t. And now I can divide the 32 into 64, and I get t is equal to 2. So I get exactly the same answer, whether I work it this way or whether I work it the other way. Now, what you should practice with are problems also where you throw an object up and you say, how long does it take to get to the top? How long does it take to go all the way up and all the way down? Well, let me remind you that the time to go up and the time to come down are exactly the same. So in fact, I can tell you without doing any more calculations that if I had thrown the object at this final velocity of 64, thrown it upward, it would have slowed down, and stopped and become 0. Then it's going faster and faster and becomes 64 again. It took 2 seconds to come down. It would also take 2 seconds to go upward. So it would be in the air, if I threw it from the ground, it would be in the air for 4 seconds if I threw it upward at 64 feet per second. So now you know enough to apply these 3 equations to any problem moving in one dimension where I'm going up or down, and you can remember those specific things. Acceleration is constant everywhere. The velocity is equal to 0 at the top. Acceleration is always constant. I can use meters per second, either 10 or 9.8, 32 feet per second squared, and use these 3 equations. These 2 come from the calculus, derivations from the definition of velocity and acceleration. This one comes from solving those 2 equations.